In this lecture, we will be talking about data exploration techniques for data mining. We will be focusing on techniques which are coming from related fields of statistics, visualization, or knowledge discovery in databases, where there have been several techniques developed for exploring data. In statistics, we will be talking about summary statistics, and in case of visualization, we will be covering various visualization techniques. And from the knowledge discovery in databases field, we will be discussing the topic of multidimensional arrays and data cubes. So let's get started. First off, let's talk about some summary statistics, which gives us already good information about our data before we are able to even see it through some approaches like visualization, where we can see all the data in one image. So for unordered categorical attribute, which is like x, and it can have values between x1 to of xk of m objects O, we can define a frequency of a certain attribute value to be defined by the number of objects which are having this value of that attribute divided by the whole set of objects. So we can, for example, see that if we have objects people, and we are having these people will be, let's say, students, and we have undergraduate students, freshman, sophomore, junior, and senior. If we have, I think, 510 of students in total, we can see that, for example, the frequency can be defined by 170 of them will have an attribute which will be a freshman, let's say 1 in case of the asymmetric attribute definition, and that will amount among 500 objects, a record of 500 students, to 0.33, so 33% if you like. And then we can also see that for sophomore, that will be who we will have this attribute only among 137 flagged with 1, then this will be 0.27 or 27%. And then for juniors, we will have 0.22, and for seniors, we will have the 18. And if we look at this is 40, and then this is together 60, so we have 100%, or in total here, if we will sum this up, this will amount to 510. So the frequency is a summary statistics, which is telling us how many of those of the data elements have this particular attribute. So that will be in, I think in this case we will have this this attribute will be simply like a year, and it will be a categorical attribute which is not really ordered, and then we will simply count this which all the students which have this attribute set to freshmen, and then it will be 170 times. So it will not be, doesn't need to be done through this asymmetric attribute with like a flag of 1 or 0, but it could be directly attribute which will have these 4 categories, categorical values. Okay, so and then if we want to find out the mode, then the mode will be like the one highest frequency which we will have, that will be the object with the highest frequency will be actually the mode. So in this case of this particular data set, we will have the freshman will be having there will be the category which will be having the highest amount of students. So in the attribute let's say, undergraduate study, which might be the title or year, if you like, in the undergraduate studies, then the mode of the year attribute will be freshman. And that's how we calculate the mode, which is the high number with the highest frequency. Okay, so these are two already useful properties which can be obtained from data through summary statistics. We will be looking at more deeper insights from summary statistics methods in the next. Before that, let me shortly introduce this one data set we will be talking about quite often in this class, and that is the IRIS data set, where the IRIS data set, which you can download from this academic website, contains just 150 entries of iris flowers characterized by 4 attributes. It's sepal length, sample width, and length, petal width, and length. And also, one attribute will be categorical, which will be which subcategory of the iris plant has been measured. So Setosa, Virginica, or versicolor will be 3 different iris plants, which will have each kind of different, slightly different sepal width, petal width, sepal length, and petal length. What are these words actually? So, and as you can see here, the flower is having this kind of, when it blossoms, it's having this kind of various leaves. And this leaf here is called the sepal leaf, and or part of that flower, where here we can measure the width, and here we can measure its length. So that's the sepal one. And then we have the inner one, inner part of the flower, which is the petal part, which has also some width, some length, and some width. So this is basically the data set, and we have 50 flowers from each species, in total 150 of these flowers. And we will be seeing how various approaches from summary statistics or from visualization help us to understand these flowers better, or this data set. So let us define another summary statistic after we already defined the frequency and the mode, and the next one will be the percentile. Percentile is for ordered or continuous attribute x, the pth percentile, xp, is the value of x such that p% of the values of x are less than xp. So this is very hard to understand, this sentence, but we have a nice example here which will already explain a lot. So for 50th percentile, so x 50%, 50% of the values x are less than x 50%. Meaning that if we are looking here, we will find out that for the value of sepal length, 5.8 is a length where 50% of all the iris plants will have a sepal length which is smaller than 5.8. And 5.6 will be 40th percentile, meaning that there will be 40% of the iris plants will have the sepal length less than 5.6. So I think this is becoming clearer, and we can see that 0th percentile means basically the smallest element in the data has the sepal length of 4.3, and then the 2.0 is the sepal width, and so on. So this is the element which is the minimal length in each category. So it's actually not, there might be not this one object, but from all sepal lengths, this is the minimal value. From all sepal widths, this is the minimal value. And from all petal length, this is the minimal value. And petal width, this is the minimal value. The maximal value, again, per attribute will be seen as the last one. So this is the 100th percentile. So 100% of all data are smaller than this value. So this is the maximal value, and for the sepal length, sepal width, petal length, and petal width. And we can see these percentiles defined here for these integers, for example. So if we have just a data set, mini data set of just these 10 numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then the 1 will be the 0th percentile, 1.5 will be the 10th percentile, 2.5 will be the 20th percentile, 3.5 will be 30th percentile, up to now 90% will be x 90% will be 9.5, and then x 100% will be 10. So this is the explanation of the meaning of the word percentile in summary statistics. We can quickly find out what are the minimal values per attribute, maximal values, and how do they vary in kind of this uniform percentile spread. The percentile will also tell us, for example, something about the median. If we have, this will be basically the median value for this particular attribute. Furthermore, we already discussed this in the previous lecture, but we will revisit it again. We will be talking about the measures of location, which are the mean and median. Mean is calculated as a sample mean because we can define some kind of underlying population mean, which would be slightly different, might be slightly different value, but hopefully very similar to the so-called sample mean. The sample mean is coming directly from the data and is simply an average value over all our attribute values, and that will give us the sample mean. Now, if we have the following sorted values, x1 to xm, then we can have the minimal, like for example could be height of children. The minimal height will correspond to x1, the maximal height will correspond to xm, and so that doesn't really have too much of relevance for this mean, because we can calculate it even from unsorted array of the attributes, but also from a sorted one. But the sorted array of attributes will be useful for calculating the median. So with this line above, we will be denoting the sample mean. With this wave above or tilde above the x, we will be defining the median. So the median is the x r plus 1 if m is odd and m is equal to 2r plus 1. This means that the total amount of the data objects, if we go across the attribute, is m, and it is 2 times r plus 1. So it's an odd number, and the r is basically the twice r is almost the full m, but plus 1 because it's odd. And so we know what the r will be. R will become m minus 1 divided by 2. And then for r plus 1, we will calculate, we will find out in a sorted array of xr's, in the sorted array of the attributes, which x is at the position r plus 1, and then we will be, so from 1 to m, which one is in the position r plus 1, and that one will be our median. And that holds for the odd numbers. If we have the set of odd numbers in our as the total number of data objects. If we have even number, then we take the xr and x1 as xr plus 1, and we average it. So this is the median for odd amount of objects and for the even number of objects. Then, besides the mean, we have also something called trimmed mean. This trimmed mean is something between somehow forming the continuous bridge between the mean and median in a way, because the mean itself is a summary statistic which is sensitive to outliers. Imagine that we have numbers 1, 2, 3, 90. The average of this 1, 2, 3, 90 attributes for these 4 data objects will be 96 divided by 4, which will be therefore 24. While clearly the 90 is some kind of outlier, and it drags the mean out of all the other values, 1, 2, 3, very far away. While for the case of the median, 1, 2, 3, and 90 will be actually 2 and 3. It will be 5 divided by 2 will be 2.5. So we will have the median will be much more closer to the overall trend than the mean in case we have strong outliers in our data. And the trimmed mean somehow can cope with those outliers because it can take out, a trimmed mean is where a certain p half percent from top and bottom is removed. So let's say 10 half, 5% is removed from the top and 5% is removed from the bottom. So overall, we remove 10% of the data from the from top and bottom, where the outliers will be either minimal values or the maximal ones, and then we perform the mean. So for example, if we have here something similar as I mentioned, but 1, 2, 3, 4, 5, and 90, then the mean is 17.5, but the mean here would be 3.5, much more kind of close to the trend, and then the trimmed mean at 40% will be actually also 3.5. So 40% means that we are now removing from 40% from the meaning 20% from the top and 20% from the bottom, and then we will simply have also from the rest, we will be calculating the mean, and we will end up at 3.5. As we have here 1, 2, 3, 4, 5, 6 numbers, the 20% from the top will be trimming the first number, 20%, sorry, from the bottom, 20% will be trimming as the high end of this sorted array of the attributes. So we will end up only with 2, 3, 4, 5, and then the average of this will be 3.5. We can see how this mean, median, and trimmed mean is playing out in our iris data set. And we can already see that if the mean and median are very far away from each other, that will likely indicate that we have some kind of some kind of outlier which is dragging the mean out away from the median. But we can see that all these values are roughly similar. Then for the sepal width, it's also not that very close. For the petal length, we can see that the median is quite different from the mean, and actually the trimmed mean is even smaller. It's not between these two. It's actually even smaller than the mean, which is interesting. And for the petal width, the same holds, which seems to be a little bit unusual. So typically, we would expect that our trimmed mean will get somehow close to the 130, but rather from the side where the 120 is. So maybe 128 would be an expected trimmed mean, but here we have 1.12, which is a little bit surprising. Now, next summary statistic, which we would like to talk about, are defining the spread. So while we have the location of the kind of the most frequent or kind of a typical value, let's say, for the median or for the mean, the average value, then for the another statistic defines us where are the other values with respect to this value of the average. And that is characterized, for example, by one summary statistic which is called the range. So range would be simply the maximal value minus the minimal value for an attribute. That gives us the full range of values which are found in the dataset for a given attribute. And then a very typical and often associated with mean statistic would be the variance. So the sample variance can be calculated as the difference from the mean squared summed up for all the objects. So this is now one attribute for one object, and here is the attribute average across all objects, and we are performing this difference here, and with the squared, it will give us the in the sum the variance, which is then divided by number of elements minus 1. The number of elements minus 1 is due to the fact that we are losing 1 degree of freedom by this mean value, which in the sample variance is different from the true variance. So this allows us, without going too much into detail, not to overestimate the variance. Actually, underestimate the variance. So if we will have here m instead, we will be systematically underestimating the variance with m minus 1. This estimate is the most accurate and closest to the true variance. Then out of variance, we can easily calculate the so-called standard deviation, which is just the square root of the variance. And as both of these quantities, statistics, are calculated from the mean, they would be prone to outliers. So if there is an outlier in the data, this outlier will be dragging the mean, and it will also be affecting the behavior of our kind of statistics around characterizing the spread, because they will be affected by this in the calculation. As we can see, the mean is appearing, and that's how this sensitivity to the outliers will propagate to this next statistic, to the standard deviation or variance. Therefore, statisticians have been working on developing a specific family of measures, both for spread and as well as for the position, which are robust with respect to the outliers, like the median is robust with respect to the outliers. And then we have some other measures of spread, which are also robust with respect to outliers. Like, for example, the absolute average deviation. So here we are not squaring it, so this difference is not squared, and thereby not amplifying this difference, especially if there is outlier, then this difference is large, and therefore this will be powered by 2, it will be even larger. So here we have only not squared, but just an absolute difference, and this absolute difference is simply summed up and divided by m. Now, the median absolute deviation is again something else. A median absolute deviation takes all the deviations, which we can see here, and sorts them. So from this is a deviation from the mean, and we are sorting these deviations from the smallest deviation from the mean to the highest, and then we will be taking the median of these absolute deviations. And that will be the result of this median absolute deviation, which is, again, a robust characterization of the spread of our data values for that particular attribute. The last robust statistic is the so-called interquartile range. So this interquartile range will take simply the percentile x75% value, which we have discussed before, and subtract from it the x25 percentile value, and that will be our range between two quarters. So the quarter less than 25 is one quarter, and then another above the 75 is another quarter, and then we have this interquartile range where the 50% of the data resides is this interquartile range. Okay, now let's have a look at other measures. We will be looking now at multivariate summary statistics, which are not characterizing only one single attribute, but are looking at several attributes and their potential relationship. So mean and median can be calculated for each attribute separately, and then we can have like a mean vector, which will be consisting of elements which are basically the means of the individual attributes. And then for continuous variables, spread can be characterized by a so-called covariance matrix S, where the Sij is a covariance of ith and jth attribute of the data. And we have seen it already before on the last lecture, where the Sij is calculated as this difference from the one attribute value from I and from the ith attribute and ith mean, and multiplying this difference with the with the jth attribute, and the mean is j. And here the k is where we are iterating through all the data elements so that we make these differences between all the elements and their respective means for that particular chosen attributes, which are forming this value in the covariance matrix. Their covariance is telling us how similar these two values are to each other. The high value in absolute values will give us the information that their covariance is very large. And that means that the spread of these attributes is somehow quite large. So at least one of them must be very large. The other one might be not as large, but together as a product, the overall variance is large. And if the variance is large, it at the same time means simultaneously that there could be a relationship between these two variables. But we don't know really for sure, because the covariance is basically characterizing two properties at once. And if we want to understand whether there is a relationship between these two different attributes, then we would need to actually normalize this information by their respective spreads of these individual variables, meaning we divide it by their respective standard deviations. By that, we will turn our covariance into a correlation, and correlation will mean only as it is normalized when it in terms of their of the spread of the individual variables, it only gives us information about the relationship. So covariance is an information about the spread of the two variables or attributes, and at the same time their relationship, but it's two things at one. And by dividing the covariance by the individual standard deviations of individual attributes, we basically distill the information about their relationship into the correlation, where the correlation, as we know from the last lecture, can be in the range between -1 and 1, and both -1 and 1 give us the indication of a strong relationship between the variables, and 0 will mean that there is no linear relationship. There could still be some non-linear relationship between those two variables, though. It is also important to mention that covariance measures that how they vary together and the magnitude of the attributes, but Sij will be 0 in case there is no linear relationship. So as I said, it measures both aspects, but if there is no linear relationship, even if the spread is big, the Sij will be 0. And if we are just having the same attribute twice here, then we can see that our covariance is basically representing us the variance of one variable. Okay, so we are now in the multivariate statistics. We have defined the covariance based on this formula, and from the covariance we derived the correlation, which is giving us the distilled information about the relationship between these two attributes, linear relationship. Now, the second strategy to explore data, which is not competing, but it's supplementary or orthogonal to summary statistics, is the visualization. Simply to plot data in some form and characterize the data in the visual way, rather than seeing just a very few numbers, very limited amount of numbers, or rather than seeing the entire table, which might be quite overwhelming. Now, the visualization is display of information in a visual form after data is mapped into graphical elements, so that relationships among data items or attributes can be analyzed or reported. This is relatively straightforwardly understood. So visualization of data is one of the most powerful and appealing techniques for data exploration, also because humans are very visual. The visual sense is our strongest sense, and it's much stronger than, for example, other senses like auditory, palpatory, or olfactory, or the like. So therefore, a lot of analysis of data relies on visualization techniques. Humans have a well-developed ability to analyze large amounts of information that is presented visually. That comes from the fact that there is a lot of visual information around us, and we are able to process this information incredibly fast. We can, with the visualization, we can, depending on the type of visualization, we can detect either general patterns and trends or outliers, or both. So we can start with looking at this visualization of the sea surface temperatures from the July 1982, and we can see the sea surface temperature of the entire world on this small image. We can see that, for example, the temperatures around Saudi Arabia, either in the Red Sea or in the Gulf, are extremely high, probably the highest from what we can see in the plot here, while the other temperatures in July have been also quite high, but then they also go even closer to the poles, close towards zero. Visualization experts would typically comment on this characterization or visualization type with this so-called rainbow color legend, because we have some kind of nonlinear perception of colors, and we can see a certain bands, like for example this yellow is kind of a tiny band here, and it looks like there is a lot of kind of information concentrated in a tiny band as compared to here, but actually this tiny band just gives us information about, let's say, 20 to 18 degrees, while the red part is giving us information from 25 to 35. So it's not that each hue is having the same kind of spread, and we should be aware of this nonlinearity, especially when we are using this rainbow color map as was used in the textbook and its associated slides. So we can see that here we have been using as a visual variable color, or the hue, because color is not only color, but we can have also the lightness of a certain hue, we can have also saturation. So all these can be somehow representing a certain variable. So here we just used the most saturated color and very bright in order to encode just a scalar information about the sea temperatures, but the visualization can be more complex than that. But visualization can utilize not only color as a visual variable, as we call it, mapped to the attributes, but it can be also position. We can encode something by position. We can call something by shape. We can encode something by orientation, width, or radius. We will see some of these in the next visualization examples. If we have some representation where we have some relationship between some explicit relationship between objects, then we can represent this relationship by an edge between some spatial points. So then we will know that these 2 points are somehow related to each other by a relation which is typical or well understood in the particular domain where this visualization was used. In case of visualization, we have several choices we can make in order to make the visualization effective. So for example, imagine if we have categorical data that is somehow put in the way that we have this just this asymmetric attribute. We can see that if we have the attributes somehow organized like this, here are 6 attributes, and we have from just abstractly named from 1 to 6, and then we have our 9 persons in some kind of arbitrary way assigned an ID from 1 to 9, we see that there is some kind of data in this table, but we do not really see any insight from here. Now imagine that we are just reshuffling in this table the columns and also rows, and we are able to find out that actually there are only 2 different types of let's say data objects here, maybe persons. Either they have 1, 1, 1 for attribute 6, 1, and 3, and then the rest of the attributes is 0, or the other way around. And now from this rearrangement, this becomes very, very clear. However, a very equivalent visualization or data representation in a tabular form might make this information not clearly standing out. This is an example how information can be very effectively visually conveyed, or there is no particular effectiveness in the visualization design. So we always should think whether there is a particular automatic representation which can help us to see some patterns and trends in the data. And in this case, this reordering of columns and rows led to that. So therefore, reordering of columns and rows is very typical for observing tabular data, but also it is typical in visualization, because you can imagine that these zeros and ones are represented just by some colored squares, and these colored squares are first just scattered around in seemingly random order. But now, after we change the row and column of these squares, let's call them larger pixels, then suddenly the information about the relationship emerges. Similarly, for example, if we have a data of graph and we decide that we put that graph somehow arbitrarily in the individual nodes, and that might lead to the fact that, for example, sometimes the graph is better or worse readable. In graphs, we are often calling the unreadable graphs hairball type of graphs, because we just see a lot of lines, but we do not really understand the relationship. Now, we can imagine that in some cases, the graph is having 2 connected regions. Let's say maybe this is a social graph, and there are 3 persons who are related to each other in this social graph, and other 4 persons which are related to each other. But between these 2 sets of persons, there is no relationship. And that is not becoming very apparent if these 2 different sets of people are superimposed over each other, or whether they are put next to each other. So a good graph layouting algorithm should be able to detect connected components of the graph where there is a relationship, and these connected components should be laid out next to each other rather than over each other. Additionally, there are several guidelines what we can do with, for example, categorical data. If we have categorical data, we can put them together, forming an area proportional to the number of elements of the attribute which is from a certain category. So we can have different categories, maybe some database of flowers, and the flower can be categorized according to color, and there could be number of red flowers, there could be number of blue flowers, number of yellow flowers, and there could be represented in visualization by an area which will be encoding how many of those flowers in the database are having the particular color. And the area which is the largest will encode naturally the information that there are flowers mostly coming with the respective color of the flower in the database. So, but for ordinal data, data objects can be displayed as points ordered according to some attribute value. So we can, for example, have them stored in some along some axis, and this data can be then placed on this axis in their right order. Okay, so these are general guidelines, and the arrangement we have already discussed, both in the case of the tabular representation or some kind of a rectangular representation. Gene expression data is often represented like this with different colors, or also in the context of graph. We explained that the arrangement is often the key to recognize a pattern. Now let's have a look at the visualization techniques which are encoding frequency of certain objects. So now for that purpose we are listing here the category of sepal length, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this should be probably something like 25, I guess, times 1, 2, 3, 4, 5, 6. So we have, I think, all the 150 elements are from our iris dataset are plotted here for the attribute sepal length. So all the plants which have been measured, the sepal length is shown here, but it is shown here in terms of now millimeters, 43 millimeters, because previously we have seen that they were in like 4.3 or something like that, or 7.9, where they're respective values. So now we have ordered all these elements, but this is not really a very powerful visualization. We can just see these numbers nicely ordered, and we can quickly maybe access like how many have been of the length 68, and then that 67 were more, and things like this. Maybe we can relatively quickly find out that the median would be around 59 or approximately at that value. However, more expressive visualization here are the so-called stem and leaf plots. And for that, you can see that it is kind of an ASCII character digit-based visualization, which is actually quite expressive. So we can see here that we are taking the digit position representing tenths as the first one. So we have 40, 50, 60, and 70 millimeter lengths, and then we have here like there is one which has 43, and then there are 4 which has 44, and then there is 1 for 45, and then 4 for 46, 2 for 47, 5 for 48, and 6 for 49. So, and we can see that obviously there are most of the sepal lengths are somehow in the 50 and 60 category for the entire iris dataset, because it's less numbers and it's less long list of numbers here, and this is a very long list of numbers. We can also decide that the granularity of showing these stem and leaf plots will be that we will have 40 to 44, and then we will have 40 to 45 in a separate row. So we can see that here we have here 40 to 44. We have just 4 elements here, and then 45 to 49 is also is much longer, in fact. And then we have 50 and 55, and then 60 and 60 to 64, and 65 to 69. And we can see that the column of 60 to 64 seems to have the most elements. So this is, as I said, somewhere the mode will be, if we discretize it in this way, our the highest frequency, if we will be performing this as a categorical, ordered categorical representation, then the mode will be with the 60 to 64 category. So this is already quite effective because it actually gives us this shape, gives us the profile, the spread of the values of a particular attribute. So we can reason about what are the most typical values and how do the values differ from each other from the same type of flower. And now this was a somewhat graphical representation, but also still based on digits. We can turn this stem and leaf plots to an purely visualization technique, which is very powerful, and it is called the histograms. The histograms are also encoding us the frequency of a certain category. So here we have again these categories, again for the sepal length, so the same what we had here in this case, and we can see the distribution, and we see that actually for 5.5 for some reason we have the highest sepal length. We have the highest amount of entries. Well, this is a little bit in the conflict with this information here, but it is unclear how this is exactly represented, because obviously it seems like there are numbers, but 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers, but we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 column. So this granularity, or this binning, as we call it, the number of bins, which is the number of rows here, has been different in this case than it is in this case, and that has led to the fact that we have suddenly also slightly different shape of histograms. So we need to be aware that based on the different set of how we put things into the bins, the histogram profile will change. They will be looking similarly, but they will not be the same. So now let's have a look at another histogram, because it's somehow very interesting that the sepal width is having a very clear, very highly frequent value, which is around 3, while there are also other values, the amount of the sepal widths, which are around value 3, are simply just overwhelmingly more than the other neighboring categories. Here in the petal length, we have an interesting pattern again. In the petal length, we have the representation, which we might call it bimodal distribution, because we have two kind of shapes here. Instead of just one type of kind of a profile, we have two of them. So there are petal lengths which are of 10 millimeters or 1 centimeter approximately, a lot of them, and then there is another set which is roughly between around 5, between 4 and 5, let's say. So, and then there is another petal width, which again seems to have some kind of a bimodal distribution. Now, the interesting aspect is that now we will be doubling our histogram representation, and we can see that the shape of this histogram is now changing based on the change of this binning. It's not completely different from the previous one, which has this larger binning. This more detailed binning is it's different, but it's a little bit forming some kind of similar pattern. The same holds here, so we have kind of more detailed information. Interestingly, here we can see that the size of the petal length has moved our the mode has moved to be somewhere between 1 and 2. So this obviously has been somehow gathered in this one bin, but now in more detail we can see it. We can see it here that it is well, actually it stays the same. What happened here, in fact, was that the 0 has been moved, so the 1 should be more like here, and then it will be overlapping rather reasonably similar. So we can simply see on this histogram a little bit more details, and the message is that the profile might look slightly different because this more detail will somehow manifest itself and provide the detail with a slightly different profile than it was in the aggregated form. And one needs to say that not only the histogram binning is dependent on the width, but also on where does the histogram bin starts and where does it end. And that will also, of course, influence the shape of our histogram. Nevertheless, the histogram is a very powerful representation of frequency. It doesn't give us the actual numbers like the stem and leaf plots, but it's much more in some way scalable, because we can associate it with certain numbers, and we can also read these numbers fairly quickly and understand the histogram details. With this stem and leaf plots, it will of course rely on the fact that these numbers will need to be of the same width, so that there is no different font will cause us some kind of a different spacing, but also it will be hard to somehow maybe relate it, and it's also forcing us to have this horizontal layout rather than the vertical one. Related to histograms is also pie chart, which is giving us some kind of not absolute frequency, but a relative frequency. And here we simply, in this pie chart, in this particular case, it is rather boring because it's showing us that there are 3 different subtypes of the iris plant, and they are all represented by 50 samples. So in total of 120 data elements in this data set are uniformly distributed among these 3 types of the subtypes of the plant, and therefore each of these eye segments has exactly the same area or angle, or however you want to characterize it. General, the pie chart is useful for characterizing the frequency in the relative sense, like how much from the whole is the particular characterization, which could be different countries, for example. Maybe if you can have information about the emissions, gas emissions of various countries can be shown in the pie chart, and it can clearly show you the countries which you are counting as the highest pollutants, for example. A very powerful visualization technique coming from the statistics domain are the so-called box plots. box plot is a characterization, a visual representation of summary statistics, in fact, where the box plot is characterized through various graphical elements which encode very specific information. For example, we can see in the middle of the box plot the 50th percentile. So where is the value? We can see that the 50th percentile, which we know now what it means, at least 50% of the value of the sepal length here, for example, are less than something like 5.8. So this is the 50th percentile, corresponding also to the median, in fact. And then we have the 75th percentile here and the 25th percentile here. And we can see also the 10th percentile here and here. And then we have also information whether there are some outliers. And in this case, we do not see any outliers plotted here, in fact, but we can see that the spread of the median value is here, and the spread is somehow a little bit asymmetric. There is a longer tail, if you like, in the higher percentiles, but we can see until where more or less the data is spread, the less than percent up and down are simply not, are somewhat below or above here, but are very little of those elements. So if we are talking about the 150 elements of this IRIS dataset, that will be 15 elements are below, and 15 elements are above of these lines. Now we can see that for the sepal width, we have actually very small spread around the width. So the sepal width is just at value 3, but very few are above 4, and very few, if at all, are below 2. So, but then petal length is, for example, having very long spread. So this is a very widespread spread defined attribute compared to the other ones mentioned. So we can see here, how this box plot, which is a relatively compact representation, is giving us an information about all these attributes, and in the same context, because we have the same values are shared for all these attributes here. And we can see that, for example, the petal width is clearly smaller than the sepal width, and that the sepal length is generally bigger than the petal length. So we see these relationships between these different attributes in a very compact representation. And we can also see that we can take it out, and we can see that our individual classes, what are the box plots with respect to these different classes. Under these classes, we understand the different subtypes of this iris flower. Like, for example, this would be the setosa, this will be the versicolor, and this will be the virginica. We can see, for example, that for setosa, our petal length, for example, is between 1 and 2, while for the other two, this information is much larger, meaning that we can clearly distinguish setosa from these other types just by this petal length. And we can see that this attribute is different, while, for example, the petal width is also in fact different, because we start here from 0 and here we start from 1. We have to be careful when we are performing visualization that if we are comparing across different views or across different visualizations, it would be good if they are somehow having the same scale, because we can easily oversee here that 1 starts here while here is 0, and we might come to a wrong conclusion. Nevertheless, this only supports even more that the separation between in the petal length is very clear here, and the setosa can be easily distinguished from the other subtypes by just looking at the petal length value, and it will be very clear if this value is between 1 and 2 that it belongs, that flower, to the subtype setosa. Now let's have a look at another very central visualization technique, which is called a scatter plot. Scatter plot is a very simple visualization technique which is using two attributes at once, and it shows us these two attributes as spatial points where we can see, for example, here that there is a lot of petal length values between 1 and 2, which is of setosa, and there is 0 of them from the other versicolor or virginica. So the petal length, as we said, is clearly separable, and petal width in fact as well. So we could just draw some kind of a circle here, and everything which will be falling into this circle will be the setosa flower with very high likelihood. And the distinguishing border between versicolor and virginica is not clearly there. They seem to be a little bit continuous, but if it's within the range, let's say the petal width is in the range between 1 and 1.5, it will be versicolor with high likelihood. And if it will be between 2 to 2.5, it will be with very high likelihood virginica. So, and this information is can be useful for very clearly finding the patterns, but it has the disadvantage that it shows us only the relationship between two attributes. So these two attributes are somehow confronted in this visualization, and together they could be used for seeing the trends or otherwise the relationship between these two attributes. But we typically might want to see what is the relationship among all the attributes, like we have seen in the case of the box plots. And the scatter plot is offering us an option in case we have a lot of visual space, visual estate, a lot of pixels to show. We can use so-called scatter plot matrix, which is showing us the various properties in a clear relationship. Like, for example, the sepal length is compared here with itself. So here is the kind of a useless information because it's the same value. Sepal length versus sepal length will just lead to a straight line, really. But which is not that informative, but we can use it, for example, for placing the legend. And then sepal length versus sepal width, we can see how these two variables are related to each other. And then the sepal length versus petal length, we can see that there is some kind of a relationship. At least here we can somehow see and discriminate the setosa from the other two. So we can, and here, for example, petal length versus petal width, we see some kind of clear linear relationship between these two attributes, and we can see something similar also going on here. So the scatter plots are allowing us to understand not only relationship between two attributes, but between all of those attributes. What we can also see somehow here is that the information is kind of doubled, because we have the petal length here, which is compared with the sepal width, but we also have the petal length here, and it's compared with sepal width. So this view and this view is clearly kind of the same view, it's just differently oriented. So if you will rotate it and mirror it, you will basically end up from this view, you will end up in the same view here. So we need to be a little bit careful about how much space are we using, but in the worst case, we could just use these 1, 2, 3, 4, 5, 6 different views of the scatterplot matrix to see the relationship between all of these views. So this information will show us basically all of the relationship between all the attributes, and this information will be redundant. The next visualization technique is the so-called empirical cumulative distribution function that can depict for us the probability that an object is less than that value similar to a percentile plot. So let's first have a look at these ECDF plots. We can see here that, for example, a value of 6, maybe 6 millimeters in our case, is associated with the probability of 0.5. So 55% is the probability that then an object will be that an object is less than that value. This means that we have like the equal chance that there will be a higher value of this attribute or lower value. Here in this case, we have like a 0 probability that an object will be smaller than 4.2, for example, and 10% probability that an object will be smaller than, let's say, 4.8. So it's very similar to the percentile plot, which we will discuss right away. And here we can see that what we are interested in potentially is to study the plot's shape. So, for example, here we can see that there is an almost equal probability that an certain attribute will be of value 2, or it will be of value 3. So both is probably 0.3% probability, cumulative probability. So this means that we have the same likelihood that an object is less than 3 as that an object is less than 2. This means that there is practically no data, new data points here, which would be increasing the probability of something bit like 2.5 being higher probability than 2, or 3 being higher probability than 3. So this likely corresponds to some kind of in a bimodal distribution, we can expect that the CDF, the empirical cumulative distribution function, will look like this, because in a bimodal distribution there is one mode and then there is another mode, and in between there are simply no data points for that particular attribute, and that will give us these flat regions. So studying the shape of the curve can give us immediately information about what is going on for that attribute. How does it look like? It gives us a slightly different shape, and it might become, the analysts might become familiar with studying that shape and interpreting its shape characteristics in a certain way very quickly. So in these ECDF plots, we can see that this relates both to lengths. So these are the lengths, sepal and petal lengths, and this is the sepal width, and this is the petal width. Interestingly, there is this probability kind of a plateau, both in the length and width for the petal part of the structure of the flower. So which gives us a clear indication that there is a certain separability possible, because this is coming, this part of the steep curve is coming from this setosa subtype, and then there is no value in between, and then again the other two subtypes have a certain increase in this probability based on the fact that there are data points of these attributes in this region, while there are no in this region or this region. So if we look at the, and you can see that the ECDF, similarly to CDF, it starts always from 0 as a cumulative distribution function and ends at 1. So no matter how the profile is, we know that at the beginning it will be 0 and at the end it will be 1. We have here another type of representation, which is also somehow in some sense similar, and this gives us information about the profile of a value. So previously we had the value rather on the x dimension, horizontal, here is vertical, and we have here the percentile, and this somehow corresponds to the same plots, but it's some kind of rotated, you could say, and it goes from the 0 percentile. It will give us the minimal value for a particular attribute. 100th percentile will give us the maximal value, and we can see that this one will be then the petal width is the profile of it is here, and we can see that there is a lot of variability going on here in this region, while this part before was flat and this other part was not as steep as before. Even more pronounced, we can see it here, where suddenly we can see that there is from a certain percentile, 40% percentile, the value is approximately 4, while for the 30% percentile, the value will be something like 15. So there is a big jump between 30% percentile and 40 percentile values. So studying these profiles can give us information about what is the kind of how do these different values change overall if they are sorted. We can see here that here is a massive change, for example, while some of the other ones are relatively flat, like the sepal width is relatively flat across all the different species and all the different flowers which have been compared in this as objects in this data set. Next visualization technique, which is often used in the geographical visualization context, is contouring. Contouring we can often see on height field, like if we are going for a hike and we will be looking at a map, the map can show us a lot of contours which will be encoding the height. And the more contours are next to each other, the more steeper the slope will be, and if we have very little contours close to each other, that will indicate that we are in some kind of a flat area. But these contours are used in visualization in all kinds of different contexts. Like, for example, here we can again see these sea surface temperatures, and we see that while we have here kind of a continuous color map, we see that these contours have kind of quantized the different colors here. And the quantization led to the fact that we can read this information a little bit better in the sense of assigning it some kind of particular values. For example, we can say that the equatorial area, with exception of the neighborhood of the South American countries like I believe Peru here, will have temperatures which are 25 or more in July of 1982. However, these temperatures will be more likely of the values around 20. And then we have the areas around 15, where here we can, for example, see an interesting aspect that the west coast of South Africa will have some colder water in general as compared to the other side. The east coast of South Africa will have warmer water in general. We can also maybe see some aspects of that the relatively the Mediterranean, south of Mediterranean in particular, close to Africa, will have warmer waters than the green, which is here, which has only 10 degrees. This looks like this maybe has not been measured in July, because the Mediterranean should be generally warmer than 10 degrees, as we could see here. Then, so this contouring allows us to see and convey quantitative information in spatial visualizations. If we have a smooth transitions, it's hard to assign a particular point in space to a particular value, because comparing the color is non-trivial for a human observer. However, if we have it quantized, at least on one side, it becomes easier to relate it, and then to read off kind of the quantitative value from that visualization. We can see that the other visualization in the geographical context, but also in other contexts, could benefit from something called small multiples. The small multiples is a visualization which is showing you, for example, a weather information, some maybe temperature or pressure, I don't know which attribute is shown here on the world map, but we can see its development over the entire year, and we can clearly understand how does the attribute vary in which regions and over the year. And this, in principle, this visualization can be also shown in some kind of animation. However, in animation, going through this month in a more smooth way, we will see how these patterns are moving, which will be advantageous. On the other hand, we will not be able to compare, like for example, January and August at the same time. And we can, in a static visualization, we always have the advantage that we can stare at the static pattern as long as we want. And in case of animation, this static pattern is quickly replaced by another pattern, as in a dynamic animation, and we cannot have sufficient time to study it and understand it. So now, for example, we can spend some time in understanding that this black belt here around Antarctica is somehow changing in February, becoming less prominent, but it comes into play back in March, and in April and in May and June it's still there, but somehow in February it felt like it was kind of less pronounced. And then but there is, however, also some kind of white pattern going on here, which was not observed in the coldest months of December and January. So the small multiples allow this kind of analysis, and it will be more difficult to do it in a fleeting animation, because this information will be quickly disappearing and will be hard to make this conclusion. If we want to visualize high-dimensional data, we will often resort to some kind of abstract visualization, like, for example, here, where we are representing our 4 dimensions. So this is not really high-dimensional data in that sense, because it's only 4 attributes, but we have this for high-dimensional data. This is also well suited, and we can perform visualization with using colors. And what we are showing in this visualization here is that we have our all 4 properties shown in this representation, and they have generally different different values. Sepal length is different from sepal width, the range. However, we assume normal distribution in these measurements, and we will normalize it or standardize this normal distribution to the distribution between 0, 1. So the mean is 0 and the standard deviation is 1. For 0, we have some kind of a color which is of this cyan character, and then higher value is towards red and smaller value is towards blue. And we can see here how do this distribution of these individual attributes, how does it look like. So for example, for setosa, we can see that the with the blue color, that we are consistently below the mean with our sepal length. And with petal length and petal width, or even more so. So here, this is not so clear. Sometimes we are reaching the value of the mean, but in the case of petal length, we never reach the value of the mean. We can also see that compared to that, for sepal width, we are actually sometimes exceeding the mean. Sometimes we have very high values. So overall, we are above the mean in case of the sepal width for the setosa iris flower. And we are somewhere around the mean or below for the versicolor, and we are below the mean for the virginica, for the sepal width, which is interesting, I find. Maybe they have switched this because maybe the setosa is generally smaller, but we would need to check that whether this visualization is actually correct or not. And then we can see all these attributes where, for example, the setosa is well separated, and then for versicolor we see that we are somehow in the mean values for the petal length and petal width, and for virginica we have very high values for the petal length and width. And another type of this kind of heat plot visualization or matrix visualization. So with this, we can basically visualize the data matrix. This conveys high-dimensional data through matrix plots. So this matrix plot is very useful, but in order to have somehow some common legend, we would need to, therefore, each of the attributes would need to be normalized to the same distribution between 0 and with 0 mean and with 1 standard deviation. We can also look at correlation plots, and we see correlation between here this is maybe an absolute value of the correlation, I would assume, or maybe it's trimmed and the negative correlation is not here shown, but we can see that there is not a linear relationship, these are all the same comparisons. Virginica correlates with virginica very much. However, the setosa is not correlating very much with the versicolor overall, and it's not correlating very much, even less so, with virginica, because we see more and more blue coming in, so indicating that there is no linear relationship. However, these two are not so dissimilar, and what we can also see here, where the versicolor and virginica are somehow strongly correlated with each other, indicating that this red color really is indicates some strong correlation. So these two subtypes, virginica and versicolor, are clearly more related to each other than the setosa, at least in terms of the phenotype. We have already mentioned that this is useful for for high-dimensional data, and it is useful when the objects are sorted according to the class. So we have here the information about the classes, and that allows us to compare the class of Setosa with the other classes and see the color. If we do not have the class information, it might be relevant to reorder the different objects in this way that there will be similar values will be next to each other, and that could lead to an insight where we can see that some elements of our dataset clearly form a separable cluster from visually from the other data elements in our dataset. If we want to perform these matrix plots, we would need to normalize the attributes across each other so that no attribute is dominating the plot. In the correlation, this is already done because we are dividing in the correlation by the standard deviation. So the correlation is always between 1 and -1, and but in this case between 1 and 0. Plots of similarity, which is the correlation, or distance, can be matrices are useful for visualizing the relationship between objects. So this is the second case. Here we are directly showing the information about the particular attributes, while here we are showing it indirectly in sense of correlation, where we are relating this attribute to some other attribute. Next visualization technique is called parallel coordinates. In this visualization technique, as it is called parallel coordinates, the coordinate axes will be all parallel to each other. And we can see here that here is one axis of values for sepal length. Here is another, would be another axis, but it's not drawn, but could be there with the same. In this case, it will be the same values. However, it could have its own axis of values, for example, which was not used here, so that it gives prominence to these profiles. And we see that for each petal width, petal length, sepal width, sepal length, we can see the parallel coordinates, how they look like. And this information actually shows that each data element is one line within this plot. So it's not a point like in scatter plot where object will turn into a point, but an object turns into a line here because our axes are parallel to each other and not orthogonal, as it was in the case of the scatter plot. We can see here that, for example, for the Setosa, the sepal length is generally smaller than the sepal length of these other two species. However, their discriminative power is maybe not in the sepal length attribute, but clearly in the petal length. So here it is very easily separable, and also in the petal width. The same kind of holds for the other two. So the best separation between these two species is to look at the petal properties rather than the sepal ones. And we can see that sometimes some objects are here having kind of discriminable petal length, but then they will have smaller petal width. So maybe it makes sense to increase the likelihood of being of one type by observing both of these properties at the same time. Okay, now the other plot is of the same kind. The only thing which happened here was that we have replaced the sepal length here with the sepal width. We switched the two axes, and we can see that instead of here kind of observing a more difficult profile, we can see here that the profile becomes kind of more monotonic, if you like, and it's maybe easier to follow the lines of the individual objects. So for example, here we can see that there is one object which is clearly having a very small sepal length, but it's of the type of Virginica, but then it is kind of discriminable from the petal width here, because it's kind of already getting into the range of the higher values of petal width than the most of the versicolor objects or flowers will be having. So these parallel coordinates are also useful for high dimensional data visualization, where the object is represented by the line, and the attribute values of each object are plotted as point on each corresponding coordinate axis. The points are connected by this line forming that object. The ordering of attributes is important so that we can see groupings, and therefore it should be supported by the system to reorder the axis, or automatically order the axis. Last visualization metaphor is also suitable for high dimensions, or at least multiple dimensions, and it is generally known in the visualization literature under the term glyphs. Glyphs are a multidimensional encoding of points, so are augmented points, often in spatial visualization, where each point will have will be encoding some kind of pattern. And we can see that these glyphs can have different designs, and they can convey multiple dimensions through its shape and other visual channels. So it could be based on color, based on shape, based on various geometrical elements. And under this category, one type which we will discuss are the star coordinates. So the star coordinates are a specific example of glyph showing 4 properties simultaneously. We can see that there is some kind of center of this star, and then in each direction we will have one dimension. Like for example, this element, it is showing us a particular flower with this star, where its sepal length is of this length, sepal width is of this width, petal length is of this length, and petal width is of this width. And we can see, based on the different shapes, that the setosa overall has different smaller shapes, but although the one shape which is not that different here is the sepal width. So the sepal width is similar to the other classes. So here we can see just 5 elements out of 50 setosas, 5 elements out of 50 versicolors, and 5 elements out of 50 virginicas. And how do they differ? We can see that the petal length and petal width are clearly much smaller in case of the setosa, while this is not the case for the other 2 classes. And the least discriminating aspect is the sepal width. Overall, the sepal length seems to be still quite discriminative for the setosa flower. And then these 2 classes are generally harder to distinguish. One could say that the Virginica is overall seems to be slightly larger in its proportions as compared to the versicolor. And we can also perhaps create per each class some kind of an average star shape, which we could then look at and represent it as to understand better. Maybe we could also on these glyphs represent not only the actual elements and or the mean values, but maybe also like the other statistical information. So one can think of that this could be also useful for maybe placing some kind of a box plot here here, here, and here to characterize the distribution across, not for one element, but for the entire class. So with this, we will be concluding the discussion on visualization techniques. We have seen several visualization techniques, starting from the histograms and then looking at the various percentile type of plots, box plots, or spatial views where we were using, for example, visual channels like color, but sometimes we used it in a continuous way, sometimes in a more discrete shades of colors were used in the contouring example. And then we discussed the various visualization techniques for multidimensional data, like, for example, these matrix plots or these correlation matrix plots. Scatter plots we covered also, and towards the end we also discussed these special techniques, like, for example, the parallel coordinates and the glyph metaphors, which are then useful for encoding multiple attributes at the same time. Now we will look at the techniques which are used from the database community. How can we deal and understand complex data sets by turning some of these data attributes into some kind of multi-dimensional arrays. So imagine that we have again our iris dataset here, but instead of giving exact values of petal length, width, and we only are representing it by 3 different values, ordered categories, if you like: low, medium, high, and then also here low, medium, high. And we will use it as some kind of coordinates, like in an image. Imagine that you have coordinates of an image where the pixel goes between coordinates in one dimension between 1 to 256, for example, and in another dimension between 1 to 256. For such a square image, we will have also here something similar, where we turned these attributes of petal length and petal width into actual coordinates. So there are not really spatial coordinates. These attributes are about the length of these individual parts of the flower. So it's not like coordinates in a 2D space as we would be used to, for example, in observing some part of the Earth or map in general, but we will turn this problem partially into a map. And here we can see that we are actually turning these data attributes into discretized coordinates in a multidimensional array. We have only 3 per each of these: petal length and petal width, and we can see it here. Here is low, medium, high for the petal width. For the petal length, I guess it's width here as well. So this is, I guess, wrong. We have the other axis, and then the third axis, so we have kind of a volume, if you like. We have these species. So, for example, this will be setosa, this could be the versicolor, and this could be virginica, as we can see it here. And what is stored inside these cells which we have created? Well, we will simply aggregate there how many of the elements are there from a particular species, in this case, in each kind of slice, if you like, which have both low petal width and both low petal length. And with the assumption that these values low, medium, and high have been reasonably selected so that it somehow categorizes some kind of clustered values and doesn't go across the cluster. So Other attributes, however, can still remain as target attributes and can be represented in these cells. However, they need to be somehow aggregated there. So there could be a sum, for example, or there could be an average, or simply a count. So cells also can represent count as a histogram, which we can see in this case. So if we imagine that we have seen this kind of a conceptual view from the database community, we will be looking at these different slices. So we have been length and width are here compared, and then we have counted over certain types. So here is the setosa. This will be the versicolor, and this will be the virginica. We can see that the petal width and petal width and petal length have both. Most of the values are in the low cell, while in the case of the versicolor, most of the values, not all, but most, will be in the medium cell, and in the case of the virginica, we will see that most of these values will be in the high cell. So this could be easily used for somehow discrimination of these three species. So we have converted the original data into something which we will call the fact table, and that has been also seen on the previous slide. So where we have each row will actually be corresponding to one cell, and these columns will be the discretized attributes. So even if the attributes were before continuous, we need to discretize them into some categories, like we would be doing for the histograms as well. In fact, if we have just a count in each of the cells, then it is some kind of a multidimensional histogram representation. The dimensions become categorical attributes, and the combination of these dimensions defines a cell. The content of the cell is the target quantity, which often is counted or is summarized or is averaged. Now, we have seen in this case, for example, that we have performed so-called slicing. We have sliced this multidimensional array, which was consisting of petal length, petal width, and the subspecies, into three slices according to the subspecies, and we have looked at these slices individually, and we can clearly observe that each slice has very distinctive pattern which characterizes the particular subspecies of the iris flower. And this is in general known as the so-called data cubes in the databases community, where out of this data, which is not originally very spatially characterized, it is we create spatial coordinates of some of the selected attributes. So we select which attributes should form these selected coordinates, and then these attributes will form as some kind of a two-dimensional, three-dimensional, or multi-dimensional space, which is full of cells. So, for example, it can be used very effectively in the case of some transactional records, where we can see that there are some products being sold at certain point in time for a certain price, and then because of maybe different amounts, because we can see here there is a big difference in the price here. However, this could be different amounts and at different store locations. So this information we can represent in our data cube logic as a three-dimensional array, where one array will be the product ID, one direction, which is interesting. Then another one will be the location of the store, Minneapolis, Paris, Chicago, and then we have the date as the third axis, and the rest is somehow aggregated, which is the value of the prices. And that this data cube aspect means that we have this data cube representation, and all the target attributes which we are interested in will be somehow stored in this one data cube information, aggregated based on how many of the elements sort of fit in it. And the aggregation function could be, as I said, either counting, sum, or the average. So, and here we can, for example, see how we have created within this, we have created a slice within the product ID and date we can look at it from this direction. We can look at it from all kind of directions of these different projections, from product ID versus date versus location, or product ID versus location. All these views are possible. And here we have chosen one, which is product ID versus date. And these data cubes have a big benefit that they are offering us to see this content of this cube, these individual cells as we slice through it, but we also can see the marginals. For example, the sum of all these values over the entire year, 2004, we can see that the product ID1 has been made a revenue of $370,000, while the product ID27 has made almost $4 million. And overall, revenue was across all the product IDs 227 million, and this could be, for example, either so it's not clear from this one particular view whether this could be either done through a slice, so that we see just a slice of one let's say location, or it could be the sum of all the locations, so aggregate across locations, and that could be then the total revenue across all locations. So either it is kind of a projection across all locations and summed up, or it is just a slice which will then represent just one location. So the key aspect here is that we have the ability to compute these marginals and forming the so-called cross tabulation, which is also used in statistics to understand the data. We can therefore see that these data cubes are giving us the possibility of slicing, but also of so-called dicing, as we will see next. Data cubes are can be used also for dimensionality reduction, because they offer us, through this marginalization, to somehow just represent all these, let's say, dates, to collapse all the dates of a year 2004 into just one number for one product. So the entire row or columns of the dates for 2004, which have been 365 dimensions, if you like, we have just represented it by a single number per the product. And with this, we can significantly reduce the amount of dimensions which we will otherwise need to look at. Pivoting is a special technique where the aggregation of this with this strategy is performed to all dimensions except of two, forming as a two-dimensional cross tabulation. So if we are if we aggregate across everything, all dimensions, except of two dimensions, and then we plot these two dimensions with those aggregated values, this will be called pivoting. And we can always choose which dimensions we want to aggregate which dimensions we aggregate across and which we are using for plotting these two dimensions. We have seen already examples of slicing. Then there is another technique which is called dicing, which is, you can imagine that the slicing is like a cutting slice, while the dicing will be something like a cropping a subvolume. So maybe we will just specify a certain date for a certain product IDs, and we will be cropping that as our region of interest and not be looking at the entire potentially huge table. Then, furthermore, in these multidimensional data arrays, often there is some kind of hierarchical information present. So, for example, the week can be represented together, aggregated into a month. Months can be aggregated into a year. And therefore, in our multidimensional arrays of the data cube representation, we can either, for example, drill down. So if we have just years in one axis, if we want to have a more detailed view, we can just switch from the year detail into a month detail by the method of drill down. And going back from month to year, we will go with a roll up. So these are the operations on this multidimensional data representation with these data cubes. And we can see that it works well for the temporal kind of type of variables, but also in spatial, like we can have continent, country, province, maybe city, could be different versions of this of the spatial attribute across which we will be able to perform roll up and drill down. But that also can be done in kind of categories of things which are being sold in shops, like for example clothing. So we can have subcategories of clothing, maybe for women, for men, for kids, and then under that we can have different subcategories like maybe trousers and shirts and other types of clothes. And we can understand that such a categorization can be also done in the electronics and in the furniture, and all these kind of hierarchical representation can then be interactively explored by either rolling up or drilling down to see some more details. So with this characterization of the multidimensional data analysis by this method originating from the knowledge discovery in databases, we will conclude the exploration data lecture, and with the lessons learned that there are various areas in let's say statistics, visualization, or databases which have developed their own approach how the data can be explored. And we have for our data sets, if we want to understand what is sort of present in them, we have all this toolkit methodologically available, and we can use it in our daily analytical tasks or in our studies of data sets, which we will also have in the course of this course. This concludes the data exploration lecture from the data mining perspective within the course on data analytics.